All right, the last part of section 10.5 is deals in surface area. So we're going to deal with surface area and polar form. Now this is going to be very similar to the surface area from going from parametric form when we dealt with arc length and parametric, and then we go into arc length and we go into surface area and parametric. It's basically the same thing. Okay, so what we're putting out in front here, we're taking our arc length formula, square root of this stuff, integrated from alpha to beta, and we're going to throw on, because we're rotating it 360 degrees or 2 pi radians, 2 pi times, well, depending on which axis we're rotating it around, it's either going to be a y value, like it is here. If we rotate it around the polar axis, which we would call the x-axis in rectangular coordinate system. So if we revolve it around the x-axis or the polar axis, we have to use a y value. Remember, y is r sine theta. And if we have to rotate something around the y-axis, which is the line theta equals pi over 2, then we'd have to use an x value here. So we'd use r cosine theta, which would be our x value. So surface area and polar form looks a lot like arc length, but with this 2 pi, either x value times the square root or 2 pi y value times the square root, obviously integrated all from a to b, or alpha to beta. So what I'd like you to do, that's a pretty straightforward calculation. I'd like you to push pause on this video and try to find the surface area for this curve revolved around the given line. So we're going to take this curve, we're going to revolve it around the polar axis. Okay, that's the x-axis in rectangular coordinate systems. So push pause and do that. So because we're rotating around the polar axis, we're going to use f theta sine theta. Now remember, our r is cosine theta, so the derivative of r would be -6 times sine theta. Again, derivative of cosine is negative sine. Now here's where people get confused, especially when we're dealing with trig functions as our r equals. This r is just my f theta. So when I plug this in, I'm going to have 6 cosine theta here, but I'll still have this sine theta here. I'll put 6 cosine theta in there. I'll put -6 sine theta in there. And we get an equation, or excuse me, yeah, an integration that looks like this. So 6 cosine theta times sine theta out in front of the square root. Underneath the square root, we have 6 cosine theta squared plus -6 sine theta squared. We have a 2 pi out in front of that. And then this problem told me to integrate from 0 to pi over 2. When I put all of that in, I get a surface area of 36 pi, which is about 113.10. By the way, the reason you get such a nice surface area is that what we're creating is part of a sphere. We're actually doing the surface area of, excuse me, of part of a sphere there. So that's why we're getting this really nice surface area. So that's the deal. Surface area, again, pretty straightforward. This takes a minute to type into your calculator, but everything other than that is a pretty straightforward process. So I want you to do one more. Push pause on the video and go ahead and do example 9 on your own. All right, this time it's said to revolve around the basically y-axis, which is the line theta equals pi over 2. So we have to use f theta cosine theta in this spot underneath my square root. It's the same kind of concept. So start with r. R equals e to the 5 theta. Derivative of that is 5 times e to the 5 theta. You just bring that 5 out front. So f theta, put in e5 theta there. F theta, put in e5 theta there. F prime theta, put in 5 times e5 theta there. The problem told me that my integration is going to go from 0 to pi over 2. And so you put this whole thing in your calculator. Again, it's kind of a messy process, but a messy type in. It's a pretty straightforward thing, just messy. And you end up with 210,214,874.87. So what is that? That's 2,104,874.87. If you try to divide that by pi, doesn't really come out to a nice number. So we'll just leave it as is. So there you go. That's what's happening as far as surface area goes. By the way, this is such a gigantic number because if you actually graph this from 0 to pi over 2, you get a gigantic curve because of the increase. This is, again, exponential growth. So there you go. That is how to calculate surface area with polar coordinates.